The next report will be made by Mathias Rothermel from Shtuttgart University of Germany.
Okay, thank you for the introduction. My name is Mathias Rothermel. I'd like to welcome you. And I want to talk about SGM-based 3D reconstruction from Oblique aerial imagery. This is a slight change on the title of your programs, but I hope that's okay. Okay, I want to start with an overview, like I want to give a motivation, speak about the implemented pipeline, which is in fact image rectification, then the actual semi-global image matching, disparity map fusing, or multiview triangulation. And I want to speak about tests and results. First, the data set, so imagery we used, the test on stereo matching, where we actually look at the plane stereo matching technique, and some results on the disparity map fusion. And I'll close the talk with a summary and further work. Okay, so to the motivation. So far, the semi-global matching technique showed pretty impressive results for nadir configurations of aerial imagery. We have pretty short baselines there, and it's not convergent shot, it's also here's some little examples. And what you can get is pretty dense point clouds and rather nice geometry. The problem here is for some applications you perhaps want to have like some facet information, and it's pretty hard to get this in the nadir shots, or you can only just sparsely reconstruct that. Okay, so we continue. I'll give an overview over the implemented pipeline. As input, you have the images and exterior, interior orientations, do some image undistortion, and then you do the epipolar image generation, which is some kind of projective warping of the images. Then the actual dance matching happens, and from these results, you do the triangulation, like the extraction of 3D information. And your final result will be a 3D point cloud or a depth image as you want. Okay, so first step, image rectification. The overall goal is to speed up your matching process. And what you do is do some projective plane-to-plane warping in a way that pixels representing the same world object point are in one line. So epipolar lines are horizontal. Also, they are located in the same row. So actually, if you want to search for correspondence pixels, you only have to search along the epipolar line, and this is a one-dimensional line in the image. Okay, then we have the semi-global matching. Was introduced by Hirschmüller. I just want to talk more generally about it in the beginning. So the task is to find correspondence pixels in the images. So for example, you have the pixel representing the top of the church, denoted by P. You want to have the correspondence Q in the match image. Since we did this stereo rectification, we only have to search along the epipolar line, horizontal line, and you can easily denote like the actual position by some value here, disparity, so some also say parallax. And if you do that for every pixel, you get an estimation of disparity for every pixel, or nearly every pixel. Okay, we had this formula in some of the talks before, or one talk at least before, and generally this problem of finding correspondences can be expressed as some global cost function. The problem is that it's really hard to solve, like it's NP hard and it takes a long time to calculate the solution. Anyway, you have the data term, so actually which similarity measures of the gray values in your image, and also a smoothness term which guarantees you like smooth surfaces. How does this semi-global matching work? First, we define some function or similarity measure, denoted by C in here, which actually represents the goodness of the assignment of a base image pixel P and its correspondence or potential correspondence in the match image Q. So if you take a look at this one here, you have this base image pixel P, and we're looking along the epipolar line and calculating like the cost for the similarity. And each of these costs is stored in a so-called 3D cost structure. So we assign it in there, and for sure we can do that for every pixel in the base image in here. And somewhere along this cost string you have your minimal costs. And now you could say, okay, these minimal costs represent somehow my best disparity estimation. The problem is these minimal costs are not that distinctive and result in wrong disparity estimations. The solution is doing some cost aggregation within these three-dimensional cost structures. And this is, for example, you do that along 16 image paths. And for example, we look at how are the final costs of these potential correspondences calculated. So you take the proximate cost values and you do some sort of weighted summation of the cost contained by the cost cubes. You also introduce some penalty terms in here to force these things to be rather continuous. That also will guarantee you like a surface that is rather smooth. Anyway, you can do that for every path in here in your cost string, and you can do that for every potential correspondence in here, which will give you the final costs. And now you can just simply pick the minimum of the string, and this will give you the disparity estimation. Doing that for every pixel, you get the parallax image or the disparity image. Now I want to talk shortly about the disparity map fusion, multiview triangulation. And the surface is captured redundantly, normally, or for sure. You have the base image, and I assume you have an object point. You have a match image 1 where it's captured, a match image 2, a match image 3, and you have this disparity estimation, redundant disparity estimations. So we fuse them in the end, and this has the benefit that outliers are efficiently removed, and also the accuracy is increased. Doing that, this fusion step results in your final depth map or your 3D point cloud. Okay, a little bit more in detail, what do? You have your disparity estimations in match image 1, match image 3. You have the base image. You define some confidence interval in image space. Just project that on the ray to find an object space. And this will give you a range on this ray. If the ranges are overlapping, then you say, okay, it's geometric consistent and it's not an outlier. After you have this set of consistent measurements, you just apply some Levenberg-Marquardt approach to minimize the geometric error or the reprojection error. So yeah, that's basically, you estimate, it's an iterative approach. You estimate like an 3D object point, calculate the projection in the images, divide them, subtract them from the actual images, and the 2 norm gives you the distance, and you minimize this functional. Okay, so the used data set for these oblique tests was the camera system was the Vision Map A3. I'll talk some little about the flight parameters. So the GSD of 6 centimeter in Nadia case was captured. Flight height was approximately 2,000 meters. You have forward side lapse of 55 and 44%. So side lapse is exactly this part in here. And you have these oblique viewing angles of 25 to 44 degrees. Oh, this is actually that part in here. Okay, so the flight, I try to make an airplane here. This is the flight direction. Flight was simulated with 4 mounted cameras. So yeah, looking at 45 degrees, 135 degrees, minus 45, and minus 135. And this will give you some footprints which are trapezoid. Just some visualization here. Okay, now to the test. For the test, we picked a base image, and we selected 41 match image based on the footprints on a plane. That says, okay, we have overlapping areas in here. Okay, and yeah, as you see, this is the base image. These are the match images. Okay, for the first test, it was the question: how does the implemented algorithm perform on oblique imagery, and what accuracies can be expected? So this is mainly dependent on the flight configuration, and it's not that much a matter of a matching process. Okay, so what did we do? We computed this 41 stereo models. We evaluated the successfully matched point. We evaluated the theoretical accuracy in object space. And all results are evaluated with respect to alpha mean, which denotes the average of all ray intersection angles defined by the reconstructed points and the two camera centers. I have a figure for that, but actually you can say that this is some estimation of the similarity of the image pairs. Okay, here is the figures. You have the camera centers and you have your angles right here. You have the surface, and this alpha mean is just adding these angles and dividing it by the number of angles. Okay, this chart denotes the successfully matched point in pixels, and as you can see, pretty dense results can be obtained in here. So we are in the region to 50%, like something 70 to 100%. Well, there are also some really low values, and these might correspond to these image pairs which were selected by the footprints, but doesn't actually overlap or only sparsely overlap. Okay, talking about the accuracy, therefore the normal or the formula for the normal stereo case was applied. We have the depth in here. Thereby we calculated minimal, maximum, average depth of the point clouds. And in further tests, we had some image space accuracies between 1 and 0.3 pixels. So applying these gives you this chart in here. So exemplary from alpha mean around 75 to 4.74 gives you object space accuracies in depth of 4 to 28 centimeters. Pretty interesting is here, like if you have this really small baselines corresponding to images of the same strip, you get 25 meters to 6 meters roughly. Okay. But you have to say that this one we didn't take into account redundancy of the images or measurements. Okay, the second test is about the disparity map fusion multiview triangulation. The question was what density securities can be expected for the final results, and are really all models necessary to be calculated, because this will cost a lot of time, and perhaps some models doesn't contribute too much to the final solution. Okay, for the test design, we selected 6 subsets from the 41 stereo models. According, so first subset, all stereo models providing alpha mean smaller 5. Second subset, all models smaller 10 degrees, smaller 15 degrees, smaller 20, 25, and 35 degrees. We take a look at the average standard deviation in depth, which were calculated by the analysis of covariance matrices of the actual object point triangulation. Then the number of successfully triangulated points, the average number of models used for triangulation of one object point, and the number of most models to be processed. So these are the charts in here. You have the number of processed models, average number of models used for point triangulation. You have the triangulated pixels and percent of all image pixels. And you have the standard deviation in depth, sigma d mean. Okay, as you can see, so this is unacceptable for having only 11 models with small baselines or small alpha mean. We only get completenesses of 61%. On the other hand, taking all models, you can get completenesses up to 90% and standard deviations in depth of 4 or around 4 centimeters. As you can see here, so taking only 28 models, so all models smaller than 20 degrees, you can reach completenesses close to 90% with a little less accuracy in here. And just for comparison, for all models, you would need to have to calculate 21.5 minutes, and here just 15 minutes. So yeah, it's also application dependent, but yeah. So if I would process it, I would go for the reduced version. Okay, now I want to show some point clouds in here. So this corresponds to the set of smaller 5, smaller 20, and smaller 35 degrees. Here we assigned the actual standard deviations in depth. And yeah, as you can see, red denotes bigger than or equal than 20 centimeters. Blue represents standard deviation smaller 1 centimeter. As you can see, for surfaces like streets where you don't have any texture or only less texture, you have little increased standard deviations. Matching is pretty working good for flat areas or planar areas where you have good textures, like this dirt space in here. And also some problematic areas are vegetation, because the appearance in the images largely varies. Okay, so I want to show the final point clouds on this data set. As you can see, little outliers are contained, so this is really raw point cloud in here, no filtering after the matching process, and depth fusion. Here, another example, you have 3 stereo pairs, and if you take a look at these 2 buildings, they are mapped also to these stereo pair, to these depth map, and also to these. So these are actually the same buildings. So you can expect that the surface is covered really, really sparsely. Okay, it's always hard to show the level of detail of the point cloud, so I just make some screenshots. I always also have the point clouds on my laptop, so if anybody's interested in that, we can take a look at that at the computer. So this is this area, and as you can see, cars are mapped nicely, little walls, and you hear the balconies and the small structures in here. Another example of the parking lot, just an example for density and really good resolution. Okay, so I want to come to my summary. I think, or the research show that these SGM-based matching techniques are capable of matching oblique aerial imagery. For the configuration, we did our tests on completenesses of 90% and up to 4 centimeters were obtained. Although you have to say that's a measure of internal accuracy and not absolute accuracy. It's just for getting a feeling how noisy the point cloud is. Okay, and the further work will be, since you have this disparity map fusion, each base image gives you 1 depth map, and these are also overlapping, so there is much more redundancy in there. Although we have a problem with really many points, so this will solve this problem, hopefully, reduce number of points, and exploit the additional accuracy. Then I want to thank you for your attention, and if there are any questions, I'm glad to answer.
Спасибо. Вопросы, пожалуйста. Пожалуйста.
I have a basic question to the approach. I mean, you go back with this technique to single stereo models, and we know for many, many years that if you use a truly multi-image approach, you can achieve much better results. This is a basic critique, not on your work, but on the basic underlying methodology. I really don't know why people are doing that, you know.
Why doing what?
Going back to the single stereo model, where you have algorithms which allow you to do multi-image matching simultaneously, which reduces the solution space and increases accuracy.
So the main thing is that the matching is really speeded up by this rectification method. That's the main part about that. Surely you can reproject all the object points and then just calculate your similarity measures. But we were trying to do that, and many institutes are using that, but it's a matter of speed, actually.
For me, it's a step back in development, quite frankly.
Why is that?
Thank you. Yeah, I have a company with two A3s. It's very interesting, I think, in any case, the step back that my colleague was talking about can be justified in certain cost areas, I believe. But what about, did you have a look at vectorization? Or did you just stick with point clouds?
No, I'm just working on point clouds right now, so no vectorization included in here. That will be really a further step. But this is actual measurements you're taking.
Возможно, вы знаете, что у Leica Geosystems
Maybe you know that
in Leica Geosystems, in X-Pro software, we already implemented EGM several years ago. Is it the same basic algorithm based on the Hirschmüller article, or it's another modification for the oblique images? And another question, very short, is it the same?
Yeah, so the basic
is it modified for oblique imagery or just the
so
same
there
as
is
Hirschmüller?
So there is some modification in there because you have really large differences in depth. In the Nadia case, you don't have this case. So what we do is just estimate. We use a pyramid-based approach, like starting at lower or higher image pyramids, and then just estimate the disparity ranges. That's like estimating a tube about the right surface. So you can reduce the 3D structure I was talking about. And yeah, that's basically, in other parts, it's some little modifications, but the main idea is still the same.
One question more. Was the computer memory enough for this imaginary and this high disparity maps?
Yeah, sure. So what you actually do, you can split your images into smaller subtiles. So it's not a problem.
You needed to split or use the whole images?
No, these, I mean...
The images are rather small for R3 camera.
Yeah, but so for these, I guess I would take, I don't know, 6 gigs of RAM. And yeah, you only run into problems if you have larger aerial imagery.
Если вопросов нет, еще раз поблагодарим Матиаса.
If there are no more questions, let us give a big round of applause to Mathias.